Welcome to the Insightful Professor. With this video, we continue our investigation of database design. The focus of this current video is to introduce terminology and basic concepts used in a conceptual model. In this series, we assume that the ultimate destination for our data will be a relational database. Hence, as we progress through videos, we will often refer to aspects of a relational database. Thus, the intended audience for these videos will have at least a basic understanding of relational database. In our previous video, we indicated the objectives of database design. Essentially, we provided an explanation of what we wish to accomplish through a database design process. If you've not yet viewed that video, we strongly encourage you to do so. The focus of this current video is to introduce terminology and the basic concepts used in developing a conceptual model. Our aim is to provide the viewer with a feel for these basic building blocks, explaining the role each component plays in a conceptual model or entity relationship model. With this understanding, we will later investigate how the application domain is understood by the designer and how each of the components is used to represent essential features or characteristics of that application domain. In a database system, relationships between records are captured, and such information is stored with the data. As we gain an understanding of the application domain, relationships, such as the one shown in this diagram, will need to be identified and represented in our data model. The process of data modeling shows the conceptual view of data in a system. Recall that in our earlier video, we made the point that we will follow a staged approach. The conceptual model is developed as the first stage. This model is independent of the target DBMS, and it does not use the terminology of the DBMS. Instead, it uses terminology associated with the application domain. At this stage, we are actively communicating with the domain experts and ultimate users of the system. Therefore, we wish to use the vocabulary of the application domain. This is the vocabulary familiar to these individuals. Data modeling identifies information required to satisfy the system specification. The data model will be developed to focus on what data should be stored in the database. The database specification that results from the database design process generally consists of two components. The first component is a diagram that we refer to as the ER model, or the entity relationship model. This diagram serves to represent the data structures that reflect what should be stored within the database. Effectively, what is the content of our containers? The diagram also serves as a communication mechanism between the designer or data modeler and the business users. The second component is a document that we refer to as the data dictionary. This document serves to describe in detail the data objects, the relationships, and the business rules that are required by the database. The data dictionary provides detail required to ultimately construct the physical database. Although the diagram itself conveys a great deal of information, it may not be able to precisely express all of the subtleties and requirements of the database that is going to be constructed. The data dictionary then serves to complement this diagram and provide some clarity and perhaps additional information and insight to the application domain. In this video, we will define the components that will be used in our diagram. Specifically, we will provide definitions and graphical representations for entity, relationship, connectivity and cardinality of a relationship, attributes, primary key, additionally, non-key attributes. We will introduce these components in the spirit of the entity relationship model. We've stressed the point that we will be following a staged approach. Specifically, we take a top-down approach. This begins with the development of what we refer to as a semantic model or a conceptual model. That results from gaining an understanding of the application domain. So the top-down approach is considered to be data-centered. An information system designed based on a data-centered approach should have a longer useful life than one based on a process-driven approach. The characteristics of data captured during data modeling are crucial in the design of databases and programs. Facts and rules identified during the data modeling process ensure the integrity of the data in an information system. Thus, not only will we identify data objects that must be represented in our model and database, but we will also discover business rules. Some business rules will be simple to understand and express in our model. These may take the form of an integrity constraint. Other business rules may be complex and not easily ascertained from a quick scan or view of the diagram. However, all business rules should be identified and documented during the design process. Recall that the design will include a graphical component and a related data dictionary. So the diagram may express some of these rules, but the data dictionary will clearly describe all of these and in some detail. Designing a database properly is fundamental to establishing a database that satisfies the needs of the user community. A data model captures the nature of and relationships among data. This model is viewed at different levels of abstraction as a database is conceptualized and designed. So what do we mean by abstraction? Well, an abstraction is a mental process that we use when we select some characteristics and properties of a set of objects and exclude other characteristics that, from our vantage point, are not relevant. We'll see that a data model will identify entities, relationships, and attributes. The data model we develop will be used as a vehicle for communication between the data analyst or data modeler and the members of the business or user community. For discussions with different individuals within an organization, different levels of detail will be needed. Not everyone within the organization sees the organization the same way. We will see that a data model will identify the entities, relationships, and attributes. The designer may gradually acquire an understanding of the application domain and seek to confirm his or her understanding with the business users. In some conversations or discussions, the designer may wish to ignore the attributes, while in others, attention will need to be given to the attributes. This means that the data model we develop may be viewed in different ways by different people in the organization. That's the concept of the abstraction to which we refer. The entity relationship model, sometimes called an ER model, is perhaps one of the most widely used data models for establishing the conceptual design of a database. The model was actually introduced by Peter Chen in 1976. And we cite the paper here. It was one of the ACM journals. In 1988, the ANSI folks chose the ER model as the standard model for information resource dictionary systems. So again, this kind of puts a greater plug or push for the use of the model. Now, the model, as originally developed by Chen, focused essentially on entity, relationship, and attributes. But over time, Chen himself and others such as Thierry, Yang, and Frey, whose classic work we identify here as well, added or enhanced the model in some way, adding greater detail and precision or accuracy for subtleties which may exist within the application domain being modeled. So additional concepts such as composite attributes and generalization hierarchies were later added to the enhanced version of the ER model. We will give initial attention to the basic model components as introduced by Chen in his 1976 work. In a future video, we will consider and discuss some of the more advanced or subtle components introduced by Chen and others. As previously noted, the basic concepts provided by the ER model are entity, relationship, and attribute. Over the next few slides, we will examine each of these in a little bit of detail. We begin with entity. An entity represents a class of real-world objects. An entity is said to represent anything of relevance and interest within the application domain that can be uniquely identified. These things could be person, place, object, event, or concept. Recall that the application domain is a micro-world that we wish to understand and represent in our model. One of the challenges we face when developing an ER model is to establish the boundaries and scope of the application domain. This is important as we need to determine what is relevant to the application domain being modeled. This can sometimes be a challenge. My experience has shown that as you develop a data model, if the boundaries are not clearly defined as to what constitutes the application domain, you could be including all kinds of extraneous objects that really are not directly relevant to the database that must be constructed. So we distinguish between an entity type or entity set and an entity instance. We had said that an entity represents a class of real-world objects. So an entity type is kind of like a class or a category, while an entity instance is an individual occurrence of such a type. So consider a human resources application domain. We might talk in general about employee as an entity type or an entity set. Specific instances or occurrences of this entity type might include employees such as Mo, Larry, or Curly. When examining an application domain, how do we discover what the entities are or what the entity types are? Typically, in conversation or discourse with the business users or domain experts, items that pop up that appear as nouns describe a person, place, object, event, or concept. They give rise to identifying an entity type. By the way, we'll talk about this in more detail in a moment, but the pieces of data that serve to describe the entity, those things which we wish to capture about the entity, are referred to as attributes. Now, we've used the term entity type and entity set. Entity set sound very formal. Turns out that this is the term that Chen himself used when describing entities within his classic paper. He used this term to refer to a category of objects to distinguish entity, which indicates a specific instance of some entity set. So we talk about the concept of an entity set or type being a category or a class and an entity instance. For example, we talk about dog as an entity set, which encompasses all dogs within the application domain. Fido and Spot may be specific instances of dog within the application domain, hence they are entities or entity instances within this entity type within this application domain. This distinction is actually very important to understand and recognize so that when we consider the entity mappings or the cardinality of relationships, another component of the ER model, which we will discuss shortly, it's important to think in terms both of the type or the set and also the individual instance or occurrence. That may help us ascertain precisely what this actual mapping or cardinality is. Unfortunately, some of the literature uses the term entity, but does not make a clear distinction between entity type or set and entity instance or occurrence. It's kind of left to us as the reader of this literature to determine the exact meaning based upon the context in which the term is used. Well, that's about all we're going to say about entities for the moment. There's much more when we get into the advanced features that we'll discuss in detail. Now, let's move on to another basic element, the relationship. A relationship represents a real-world association among one or more entities. Note that an entity has a physical or conceptual existence in the application domain. But relationships, on the other hand, don't have such an existence. What happens is they are associated with entities, and that's what kind of brings them to light. So a relationship as depicted in the ER model is effectively a relationship type or a relationship set. But a particular occurrence or instance of a relationship is referred to as a relationship instance or a relationship occurrence. This distinction, once again, is going to be very important as we get into some detail, in particular, when we look at things like optional versus mandatory participation. We have to understand that. In describing relationships, additional terms come to the surface. We have what's called the degree of a relationship. We talk about connectivity, cardinality, and existence. The degree of a relationship refers to the number of entities associated in the relationship. Most common would be a binary relationship, which is an association between two entity types. Note that the degree of a relationship can also be unary, or sometimes called recursive, where a single entity type is involved in the relationship. Clearly, in that case, the relationship pertains to individual instances of the type. A relationship could also be ternary, involving three entity types. In complex application domains, it might even be possible to find more than three entity types, in which case we refer to such a relationship more generally as an n-ary relationship, where we have unary, binary, ternary, and in general just say n-ary, where there could be n number of objects participating in the relationship. Ternary and, in general, n-ary relationships are not that common, but in some domains they might appear. So we will give an explanation of those as we proceed through the course materials. So as we present the graphical elements of an ER model, note that initially we will use the original notation presented by Peter Chen in his paper, But unfortunately, there's not a single graphical notation that's been adopted throughout the industry. Therefore, we will present some alternative graphical notations later in this video, and additionally when we gain insight to some of the other features. Continuing our examination of relationship, we see the term connectivity that describes the mapping of the associated entity occurrences in a relationship. So connectivity refers to the manner in which a relationship makes an association between entity types. In our model or diagram, a relationship can be considered as originating at one entity type and ending at another entity type. Note that the entity types are not necessarily distinct. That would be in the case of a unary relationship. These points of origin and termination can be defined as one or many. That's the notion of the connectivity. In our next slide, we will present a diagram to illustrate this notion. But the final points on this slide are very important as we develop our model and produce the diagram. We say that a relationship can be thought of as a generalization because we are considering the association in terms of the entity set or category of entities. However, the cardinality considers the participation of individual entities within the entity set. As Chen points out, the cardinality information is not present in the relational model. This is what he believes gives his entity relationship model a little bit more richness, enhancing the semantics beyond the relational model. Cardinality describes the constraints on the number of entity instances that are related through a relationship. The basic constructs for connectivity for binary relationships are one-to-one, one-to-many, and many-to-many. A one-to-many relationship indicates that for each instance of one entity set, there may be one or more instances of the other entity set. For a relationship between department and employee, which we are presenting in our diagram here, a connectivity of one for department and many for employee means that there is at most one entity occurrence of department associated with many occurrences of employee. So what we're seeing then is, if we look at it from the perspective of some employee instance, a given employee is employed by exactly one department. If we look at it from the perspective of some particular department, an instance of department, a given department employs many employees. So we can read this as a one-to-many if we read it in one direction. Alternatively, we could call it a many-to-one if we read it in the other direction. It's important to note that the relationship can be read from either perspective, originating from either one of the entity sets or entity types. So on the one side, the number 1 is shown on the connection in our diagram between the relationship and one of the entity types. On the many side, we've chosen the letter M to denote many. Alternatively, you may see the letters N and P being used to denote many. And there's some rationale behind this, as we'll discuss in just a moment. So in this diagram, there are many employees employed by a single department. Each department employs many employees. Each employee is employed by one department. So it's necessary to kind of step into the entity set and consider it from the perspective of the instances, or a particular instance of this entity type. What's the participation in terms of the cardinality? So observe that there's a single relationship defined here, but again, we can read it in either direction, one-to-many or many-to-one. A one-to-one relationship indicates that for each instance of one entity set, there is one instance of the other entity set. In the one-to-one case, the entity type employee parks in exactly one parking space, and each parking space is parked in by exactly one employee. So the notion of an employee being assigned one parking space and a parking space being assigned to one employee gives rise to our example here of a one-to-one relationship. A many-to-many relationship indicates that for each instance of one entity set, there may be one or more instances of the other entity set, and vice versa. In the many-to-many case presented here, the entity employee may work on many projects, and each project may have many employees. The maximum cardinality denoted in the diagram is the same here, using the letter M on both sides. This sometimes will suggest to people that, well, if X number of employees work on X number of projects, right, it's the same value, then we have the same upper limit. But this may not always hold. This is a situation where you may see it changed so that we say employee M, and then for project we say N. We use a different letter. The reason we might do this is to note that there are different upper limits or different maximum cardinalities that are possible. So some folks prefer to do that. Others will just go with many-to-many as MM. We'll talk a little bit more about this when we get to optional participation in a moment. So here we could say that many instances of one entity type are associated with many instances of another entity type. However, making a statement like that, it's a little too vague. It doesn't really tell us much about the actual association. But by focusing on the relationship from each direction, the semantics, and hence the cardinality, becomes easier to recognize and understand. So in this example, we could say a given employee, that is, take one particular employee instance from within the set and examine that. A given employee works on many projects. A given project has many employees who work on it. So in situations where the actual maximum cardinality is known, it's possible to indicate that actual upper limit instead of simply using a letter like M or N as kind of a general statement that it could be anywhere from 1 up to some astronomical number. Well, based on the comment that we made about viewing the many-to-many relationship from the perspective of an individual instance of an entity type, rather than broadly saying the entity type participates in a many-to-many, but let's look at the instance and look at it from the perspective of an individual employee or an individual project. This concept then raises the idea that there might be another way, an alternative way to diagram the many-to-many relationship. We could view it as two one-to-many relationships. So historically, there are at least two motivating factors for an alternative approach here. The data modeling software, which came to pass many years ago, decades ago, was first introduced. The data modeling software did not allow attributes to be attached to a many-to-many relationship. Yet that is a possibility, and we'll discuss that in more detail when we discuss attributes. So therefore, if you simply draw it as a many-to-many relationship, and the relationship itself has properties, you can't really attach those within a diagram. There are also limitations of the target DBMS, where collections were only recently added to the ANSI SQL standard. Looking at the ANSI SQL 1999 standard, where we start talking about object relational functionality. So in one approach, we could use it as two many-to-many relationships. So an employee has a one-to-many relationship with this thing called works on, which we represent as an entity type, and project has a one-to-many relationship with that same thing. Now we're in the realm of dealing with the basic diagram tools, where we have only one-to-many and one-to-one relationships, and furthermore, the relationship that we defined can now be represented as an entity type. So another approach represents the relationship itself as an entity when the relationship has attributes, and this is sometimes referred to as an associative entity. So you'll see in our notation chosen here that we would use the diamond for the relationship, but enclose the diamond within a rectangle, indicating that it is a relationship, but it's also the notion of being an entity. And that would allow us to attach attributes. So these are two alternative ways of representing the many-to-many relationship. And we'll talk more about this in detail when we start looking at actual examples of analyzing the application domain and expressing that using our diagrammatic techniques and components that we've been describing here. Our next component is the attribute. So an attribute represents some kind of a property or characteristic of an entity or of a relationship. Now, attributes of relationships require a little bit more of an explanation here. An attribute of a relationship typically comes about when we're talking about a binary many-to-many relationship. So attributes are not normally assigned to one-to-one and one-to-many relationships because there is no, say, ambiguity with respect to the entities involved, and we could simply take the attributes that we considered to be part of the relationship and tuck them into one of the entity types. So therefore, we're only going to see the notion of attaching attributes to a many-to-many relationship. Now, an attribute can be classified as simple or atomic, meaning that it cannot be broken down into smaller components. Examples of a simple type of attribute would be, for an automobile entity type, we might have the vehicle identification number, also called the VIN. We could have color or weight. Each one of these would hold a single value where, although it could consist of multiple characters, like you have RED for red, the idea is it's treated as a unit. It's effectively non-decomposable. An attribute could also be classified as composite, meaning that it can be broken down into component attributes. So examples of a composite attribute where we have the domain involving an address as an entity type. The address entity type would consist of things like street, city, state, or postal code. And each of those may be in itself simple, but the combination of all of these simple serve to define or compose the address. So an attribute that must be present for every instance is called a required attribute, and an attribute that may not have a value for some entity instance is called an optional attribute. I'll give you an example. Suppose we had first name, middle name, last name. It's possible that not everyone has a middle name. So that would be an optional attribute. In fact, there was one assignment I worked on where it turned out that at a university, they had made it mandatory that everyone have a first name and a last name, but we had one student that was there who had only a single name. So they had a little bit of trouble when they were saying, you must give me a first name, you must give me a last name, but they had only one name to provide. So they had made it mandatory or required, which was obviously incorrect because they encountered a situation where someone had only one name. So they had to somehow make it optional. Okay, that's quite a bit on attributes. And now we're ready to talk a little bit more about a subtlety with relationships, something called the existence or the cardinality constraint. A cardinality constraint specifies the number of instances of an entity type that can or must be associated with each instance of another entity type within a relationship. In our example here, we again refer to department and employee, and the maximum cardinality could be recorded in the documentation, in that data dictionary, but alternatively, it can be recorded within the entity relationship diagram. So note that we have different ways that we can express this. We had previously stated department was one, employee was many, indicating the many would be anywhere from one to some large number perhaps. But we can also specify it a little differently here. Notice in the first example, we're using UB and LB for upper bound and lower bound. This is showing an explicit upper bound or an explicit maximum and an explicit lower bound or an explicit minimum. Alternatively, we can simply put the range. In this second example, we say 1:10. So a department can have assigned to it anywhere from 1 to 10 employees. So we're making, again, it mandatory. It's got to be at least one, but it's also limited. We've capped it off at 10. So that's one way that we can address the cardinality constraint. We have enhancements or extensions to the diagram. We also should document this within the data dictionary, and we also could document it only within there. But then the diagram is not as useful as a communication vehicle. Well, the idea of minimum cardinality raises another issue or question to consider, whether every instance of an entity type must participate in a relation. This is the concept of optionality once again. We had briefly introduced this notion with respect to attributes, but we also can talk about not every entity instance within an entity set must participate within a relationship. So, given a relationship, it's possible that one entity either must occur, which means it's mandatory participation, or an entity may not participate within the relationship, optional participation. So consider again the relationship that we've been dealing with respect to department and employee. It's possible that some employee is currently not assigned to any department. The person may have been a new hire, and we've not yet determined precisely which administrative unit is going to be responsible for that employee. Or it could be that the person is kind of freelance, goes from department to department, and currently is in between such assignments. So in that case, if you say, to which department have you been assigned? Well, none of them would apply. So we have to have the idea of optional participation. So how do we deal with representing the existence, which is optional for an entity instance within our diagram? A couple different approaches depending upon the notation that we're using. So assume that every employee must be assigned to an existing department. In that case, in our first notation using Chen's standard notation, the department would say 1, and that's kind of an absolute. However, let's assume that it's possible that a department may have just been created and currently no employees have been assigned to that department. So now we're talking about optional participation on the other side. So what we do is we use a little circle going through the line that denotes the connection of the relationship to the employee type. Optionality could also be indicated with our upper bound, lower bound approach by indicating that the lower bound could now be 0. That would suggest optional participation. So the point to recognize here is that both notations have made accommodation for this special situation. So even though they have not agreed upon the exact manner in which the diagram will reflect optional participation, both diagramming methods here recognize the importance of being able to reflect that, because that's a characteristic of something that is subtle but exists within the application domain. And our goal is to produce a representation that is as faithful as possible to the application domain, regardless of how obvious or how subtle some of the characteristics might be. Let's take a look at the two notations that we've just presented and look at a more complete or comprehensive diagram and discuss it in a bit more detail. First, we'll start with Chen's notation. So in Chen's diagram, notice we're using the diamond for relationships, and in this case, wherever it's mandatory, we just simply have a solid line with some cardinality attached to it. In the case of, in general, of a 1 or an M for many. In the case of the binary 1-to-1, here we changed it a little bit from what we originally introduced, because previously we had not discussed existence or optional participation of an entity type. It's important to recognize that in a 1-to-1 relationship, that is likely to occur for at least one of the entity types. Therefore, we expand our diagram here to show that an employee may park in at most one parking space, but may not park in any. It's possible that an employee doesn't have a driver's license or doesn't have a vehicle to drive, so he or she has no need for a parking space. But a parking space will always be allocated to exactly one employee. That way we'll have no controversy, no concerns, no arguments if two vehicles arrive at the same time. One of them clearly is targeting that parking space and allowed to park there, the other is not. Now, in the alternative notation with the crow's foot notation, what we see here is we're using a solid line through the relationship connector to show that it is a 1, and a second solid line to say that it is mandatory. Notice that with our relationship here with parking space, we're drawing it a little bit differently by using that 0 through the, or the circle through the line to indicate optional participation. And the many to many, we simply have the crow's foot notation to indicate the many cardinality. With this video, we've introduced some of the terminology and components used in developing a conceptual model. The focus of this current video was to introduce the basic components used in an entity relationship model, or ER diagram. In future videos, we will see that there may be different types of entities, different types of relationships, different types of attributes, depending on the nature of the application domain. So future videos will address other aspects of database design and also introduce additional elements to our entity relationship diagram to support those additional aspects. So in particular, we will explain how to identify the entities and relationships in an application domain, how to actually do the data modeling. We'll examine additional components that enhance the entity relationship model. So if you found this video useful, consider giving us a thumbs up. Consider subscribing to the channel to be notified when these videos have been posted. If you have any comments to offer, feel free. We'll take a look at those and respond to those as appropriate. And once again, thanks for watching.